Hello, multivariable calculus students. This is Mr. Johnson, and this is section 10.4, and I'm going to talk just briefly about the components of acceleration. So we're sort of in the middle of this section, and this is a bit of a supplement to what we're trying to work on here. This is something that you do not need to recreate. This is just a little bit extra, and as I've said in our course, I want to make sure that I provide you some of the reasons behind some of these formulas, and that's why this video exists. So don't be overwhelmed by this. Just please take away something from this, and also just, as we work through the components of acceleration, which we'll do in the next couple examples in the notes, this is where these formulas come from, and my goal is that it makes a little bit more sense of what we're actually finding with these formulas. So first off, I have a little picture here of a particular curve in space, r of t, and the acceleration vector in yellow. And so when you think of a vector of any kind, you have two different components. So now we're working on just a single plane. I'll discuss this in the next video when I cover the remaining examples in this section. But the acceleration is always going to be in the osculating plane. And again, I'll talk about that a little bit later. So we're dealing with just a single plane here. And since the acceleration is in the osculating plane, it only is connected to the tangent vector and the normal vector. It's not connected to the binormal vector because you could maybe even envision that coming out of the page at you. So we're looking at just this single plane with t and n, those two vectors. Now with the acceleration, we know that like any other vector, it has two components. And so we're going to look at the component of acceleration in the direction of t, so in this direction of this green one, and we're going to look at the acceleration in the direction of n. And these are called the tangent component of acceleration and the normal component of acceleration. Now remember, with the tangent vector and the normal vector, they're both 1 unit in length. With the acceleration, that usually will not be the case. So in other words, with the acceleration, we're often not going to go 1 unit in this direction and 1 unit in that direction to get to the acceleration. We're often going to go at some sort of scalar of that. So in the end, what I'm trying to communicate is that the acceleration vector is really some scalar of the tangent vector plus some scalar of the normal vector. And if we were to combine those, we would have some vector A, some acceleration vector, made up of these two scaled components. Now the scaled components are going to be the tangent component of acceleration and the normal component of acceleration. And that's what I'm going to show you right now. So in our notes, we have the formulas for these two. And in my mind, these two formulas seem a little bit sort of abstract and outside of the norm. And so I wanted to show you where they come from. And I wanted to show you simply just what they're actually doing. So the two formulas we're calculating are the scaled components in the direction of the tangent vector and in the direction of the normal vector. So that's what we're trying to gather here. Okay, we're going to start off with a few things that we've already been studying. The first definition I'm going to put down is that the tangent vector is equal to r prime divided by the magnitude of r prime. Now what I'm going to do is I'm going to convert most of this into velocity and acceleration, just because we're dealing with the tangent component and the normal component of acceleration, so we might as well talk about velocities and accelerations and just motion in space in general. So what I'm going to do is I'm going to take the tangent vector, which is equal to the velocity over the magnitude of velocity. I'm just going to rearrange that slightly. So what we get is the velocity vector equal to the magnitude of the velocity multiplied by the tangent vector. So I'm just rearranging it algebraically. And then I'm going to take the derivative. Now remember, we're using motion in space, so our variable is t. So I'm going to take the derivative with respect to t. And when I do that, when I take the derivative of velocity, I get the acceleration vector. Again, that's kind of our whole point here. And then by the product rule, I get the derivative of the magnitude. Now this is, that in and of itself is an interesting statement, because this is not the magnitude of v prime. It's the derivative of the magnitude. So that magnitude, if it was a constant, would have a derivative of 0, but often the magnitude of a vector will have, in this case, t's in it, and it would be the derivative of that result. So we have the derivative of that times t plus the magnitude of v times the derivative of t. So we have just the product rule here. Now, as a side note, we'll just put remember so that this comes from past definitions. The normal vector is equal to the derivative of the tangent vector divided by its magnitude. So it's a unit vector in the direction of t prime. And I'm going to rearrange this one as well because I'm going to use just a quick substitution to rewrite this. Okay, what I'm going to do is take this element, this representation of t prime, and I'm going to put it into the formula right here. And so what I get in return, and this is sort of our first big formula here, is that the acceleration is really the magnitude of v and a derivative of that with respect to t multiplied by the vector t plus, and then again what I'm going to do is take the magnitude of t prime times n and put it into this equation here for the derivative of t. So I get the magnitude of v times the magnitude of t prime times the vector n. Now if you compare what I've written here with what I wrote over at the beginning, right over on the right side over here, what you can see is that I have the vector t, the vector n, and so right now we actually have an initial definition of the tangent component of acceleration, and we also have an initial definition for the normal component of acceleration, which I think is kind of an interesting phenomenon, and also just an observation, is that we now have actually a representative scale for these two vectors, which represents the components of acceleration. Now again, what I've outlined here are two numbers. This is a number, this is a number, and all it's doing is it's scaling the two different directions of acceleration. So again, acceleration is made up of the tangent vector, the normal vector, and so we've just simply scaled those to fit the vector that we're looking at here, okay? Now, we could certainly use these two formulas, and there's nothing wrong with that, especially this first one. I think this one's actually a relatively easy one to use. I mean, you have to figure out the magnitude of velocity, and then you have to take the derivative of that result that you get. This one over here is actually pretty cumbersome because the magnitude of t prime and then multiplying these magnitudes together, this is pretty cumbersome. And so what I'm going to do now, and this is what's in your notes, I'm going to show you where the notes or the formulas in your notes come from these basic ideas that we've developed so far. So let's go ahead and start maybe with the one on the right. So I'm going to start with this one, and we're just going to come up with a general idea of how to calculate this using velocity and acceleration. So the first thing, and I'll just put remember again because this comes from our previous formulas, this is the curvature, which is the magnitude of t prime divided by the magnitude of the velocity. We had it written as r prime in our notes, but again, we're kind of changing our view to velocity and acceleration given our current situation here. So we have the magnitude of t prime equal to the magnitude of the velocity multiplied by the curvature. And the reason I'm going to use this formula that we've used in the past is that I'm going to take this and substitute it in for the magnitude of t prime right here. So if I'm looking at just the element, just this element here, this scalar of n, I'm going to now rewrite it. Instead of the magnitude of v multiplied by the magnitude of t prime, I'm going to write it as the magnitude of v multiplied by the magnitude of v multiplied by the curvature, which is obviously the magnitude of v squared multiplied by the curvature. In your notes, this formula is actually written in there. So we've actually gotten into the first formula that the book provides. And again, we could use this formula. There's nothing wrong with that. I'm going to tweak it again because I'm going to take a look at curvature, and we're going to reduce this formula. So let's go ahead and remember another formula for curvature, We have many, many formulas here. So curvature also has the formula, the magnitude of V crossed with A divided by the magnitude of V cubed. Now remember, when we first learned this in curvature in section 10.3, we used R prime and R double prime. Again, I'm just converting this to velocity and acceleration. So what we'll do here is take the formula that we have, which is the magnitude of V squared multiplied by the curvature, and I'm going to substitute in for the curvature, and we get the magnitude of V crossed with A divided by the magnitude of V cubed. And you can see that we can actually simplify this a little bit. And what we get is the magnitude of V crossed with A divided by the magnitude of V. And that is your very first formula, or I should say the formula written in your notes for the component, the normal component of acceleration, or in other words, this is the scale of the vector n. So in your notes, and I'll outline this in the next video, you have a few of these other formulas embedded in the notes, but this is the one we will primarily use. And I'll show you how the normal component is actually really similar to this in terms of its setup. The operation is a little bit different, but this is the normal component of acceleration, and it gives you a number. Okay, let's go over and take a look at the value that we would multiply the tangent vector by. Okay, so what we have here is the magnitude of V, the derivative of that, and so we're gonna have to try to write this in such a way that we can actually calculate the formula. We're going to start with what we had earlier in this little, I guess you would call it a proof. So earlier in this, up at the top of the page, we had this definition of velocity. What I'm going to do is take and multiply both sides by acceleration. So I'm going to do the dot product of acceleration here over on the right side. Instead of doing acceleration, I'm going to use the equivalent of acceleration, which is the formula where we are starting with acceleration right here. So I'm going to use all of this to represent acceleration. So I'm multiplying both sides by acceleration. And I have the magnitude of V and its derivative multiplied by t plus the magnitude of V and then the magnitude of t prime and then the vector n, like that. And so what we have is V dotted with A, and I'm going to distribute now. And so what we get is magnitude of V and its derivative, and then I have t dotted with t. So again, what I'm doing is I'm distributing this through to these terms, plus the magnitude of V squared times the magnitude of t prime times the vector t dotted with the vector n. Really messy here. Now, we can actually simplify a great deal of this. So t dotted with t is actually 1, and t dotted with n, if you remember the fundamentals of this, these are perpendicular by definition, therefore it's 0. So we can simplify this entire equation to be V dotted with A equal to the magnitude of V multiplied by the magnitude of V and its derivative. And we can then solve this for the magnitude of V and its derivative, because again, we're trying to make the substitution way at the beginning of this. We're trying to figure out what does this actually mean. So we have that equal to V dotted with A divided by the magnitude of V. Now what we have here finally is the tangent component of acceleration. Now when you compare these two, they're really similar, which is actually kind of helpful when it comes to memorizing these formulas, because the tangent component is simply V dot A divided by the magnitude of V, and the normal component is the cross product of V and A. Now we have to do the magnitude because it's a number, divided by the same thing. And so they're very similar, but there's the two different components of acceleration. So if you were to put all of this together, the acceleration itself is going to be v dotted with a divided by the magnitude of v, and that's multiplied by the tangent vector plus the magnitude of v cross a divided by the magnitude of v multiplied by the normal vector. So that's the idea behind the tangent and the normal components of acceleration. Thank you.